In computer science, we'll often hear the term tree be used. But what exactly is a tree? To talk about trees, we have to first talk about what are called graphs. So a graph, it's a collection of nodes plus edges. So for example, here's a simple graph. Let's say I have nodes A, B, and C that are all connected together, or that have some connections between them. A, B, and C are my nodes, and there are edges or links that are connecting these pairs of nodes. With graphs, edges can either be directed, so I can have an edge that has directionality. This would be a directed edge. And you can think of a directed edge like a one-way street. I can only go from node A to node B, but I cannot go backwards. Versus we can have undirected edges. For example, here, let's say this is undirected. Think of this as a regular two-way street. I can go from A to B, and I can go from B to A. So hopefully you noticed that this simple graph that I drew is actually exactly a linked list. If these edges are undirected, this would be a doubly linked list because I have ways of going forward as well as backwards. And if these edges were directional, they were directed edges, this would be a singly linked list. So basically, a linked list is just a chain of nodes in sequence. I have n nodes, and I have n minus 1 edges between them that are just directly connecting them in a straight line. Okay, so what's a tree? So trees have two properties. So they're graphs, just like a linked list. A tree is a graph, and it has two properties. First, it has no undirected cycles. So with graphs, I could theoretically have a graph that looks like this. Maybe I have A, B, C, and then A. So in this graph, this is called a cycle. I can go from A to B, B to C, and then back to A. So there's a loop, and that makes it a cycle. So this is a regular cycle. What's an undirected cycle? So this was an undirected graph. All my edges were undirected. But let's imagine a directed graph. Let's say I had A to B, B to C, and then A to C. So the same links, but now they're directed. So A goes to B, B goes to C, and A goes to C. This actually is not a regular cycle because I cannot start at A and end up back at A. And likewise, I can't start at B, travel, and end up back at B. If I start at A, I can only go A to C and then get stuck, or I could go A to B to C and then get stuck again. From B, I can only go B to C and then get stuck. And from C, I'm just stuck right off the bat. So this is not a cycle. I can't start somewhere, go around my graph, and then end up back where I started. But an undirected cycle is a cycle that would come about if I turned all of my directed edges into undirected edges. So if I convert each of these directed edges that I had into undirected edges, I get back this original cycle I had. So this would be an undirected cycle. So a tree cannot have undirected cycles. Also, a tree has to be connected. Basically, if I had a tree that was an undirected graph, there should be some path from any node to any other node. So let's actually maybe take a look at an example of a tree, and that'll make it a little more clear. So here I have a tree that maybe I have 10 here I have 5, and then like 15, 3, 7, maybe this is 13, and let's say this is 20. I just arbitrarily pick these numbers. First of all, we see this is indeed a graph. It has nodes, all of these nodes, and it has edges connecting each of these nodes. Therefore, it's a graph. We see it has no undirected cycles. First of all, so I drew this as an undirected graph, but I could technically draw this as a directed graph if I wanted to. But even as a directed graph, if I converted each of these edges back to undirected edges, I would not get a cycle in the resulting graph. Therefore, there are no undirected cycles. And also, it's connected. Basically, every single piece of this tree, every single piece of this graph is connected to all the other pieces of this graph. And to show what connected versus unconnected means, let's take a look at this simple unconnected graph. Let's say I have A with B, and I have C with D. So let's say this blue graph here is another graph. This is an unconnected graph because this component of my graph, this A and B connection, is completely disconnected from this C and D connection. There are a few cases of weird graphs that are actually valid trees. So the first case that I'm going to talk about is the empty or null tree. This is the tree that has 0 nodes and it has 0 edges. So it's just an empty graph. The empty graph is considered a valid tree. So just literal nothingness. I can't even draw it because there's no nodes and there's no edges. The second weird example that is also a valid tree is a single node tree. So this has 1 node and it has 0 edges. And that would look something like this. Maybe a single node that has the value 42. There's no edges, there's just 1 node. This is also a valid tree. So 0 nodes and 0 edges, aka the empty or the null tree, which I can't draw because it's just blank, is a valid tree. And the single node tree, so 1 node and 0 edges, is also a valid tree. There are 2 general classes of trees. There are rooted trees and unrooted trees. In a rooted tree, we have a hierarchical structure where we have some sense of direction of top to bottom. At any given node, we have parent-child relationships across the edges. So a parent is the node above a given node. So 4's parent is node 1. So node 4's parent is node 1. And we have child relationships going down the tree. So node 4's child, well, node 4 has 2 children. One of them is 6. One of them is 5. So node 1 has 3 children. Node 4 has 2 children. Node 4's parent is node 1. Node 3's parent is node 1. Node 2's parent is node 1, etc. So any given node could have a parent or a child. One node in the tree will not have a parent. That is the root. The root is the top node in the tree, and it therefore does not have a parent. We also have multiple leaves, which are nodes that do not have any children. So the root has no parent. The leaves have no children. The opposite of leaves, so leaves are nodes that have no children. The opposite of that would be internal nodes. which are any nodes that have children. So in this example, 1 and 4 are internal nodes because they both have children. 2, 3, 5, and 6 are leaves because they don't have children. And we have this parent-child relationship, and we have a single root. In an unrooted tree, however, we don't have this top-to-bottom hierarchical structure. We have more of an inside-outward hierarchical structure. So we still have leaves and internal nodes, but instead of parents versus children, we have this notion of neighbors. So neighbors are all the nodes that are directly connected to you. So node 1 has 3 neighbors, 2, 3, and 4. Node 4 has 3 neighbors, 6, 5, and 1. Node 2 only has 1 neighbor, 1. Node 6 also only has 1 neighbor, 4, etc. So leaves are nodes that have 1 neighbor. So my leaves are 3, 2, 5, and 6, because each of them is only connected to one other node. Each of them only has 1 neighbor. Versus internal nodes are more than 1 neighbor. So 1 and 4 are both internal nodes because they have more than 1 neighbor.